Hey, good afternoon. Um, let's begin with our lecture for today. So again, we are in IE5320, Modeling and Analysis of Manufacturing Systems. And today we are gonna start with our first lecture on the modeling piece using a computer software. Specifically, we are gonna be learning how to use Siman Arena. Okay, so as I mentioned on Monday, our course we're gonna spend time doing some analytical models, and then half of the class will be devoted to modeling in a computer. So today we're gonna start with the modeling part, and we're gonna briefly introduce the software, some of the logic that use the software to build these models. And we're going to start with the very basic foundation for the software, and then we're going to try to build an example based on the description that we are going to be providing today. Some of you have your own laptop machines. That's good. If you don't have a laptop, we have the laptop card here with the software. Good thing about the software that is installed in the laptop card is that you get the full license for the software. In your computer, most likely you have the student version of the software, which provides some limits in terms of the size of the model that you can build. That's not the case for the computers because those are licensed. Anyway, for the type of models that we are going to be building this semester, you should be okay with the student license. But if you try to build something, let's say, I think you have up to 150 blocks, anything bigger than that, you will need to have a license. And we do have those licenses here in case, like, for example, in your project or something outside, let's say for the thesis work, you end up needing a model that is in terms of size large. You can use the software licenses that we have available. So first lab, I'm recording the lecture. I like to record these modeling lectures and then post the link on Canvas in case you forgot something or you are not clear about something. You can always watch the video, and hopefully that could clarify your concepts. So we're going to start with some basics. I think some of you are familiar with simulation already. So this concepts might be familiar with them. These are important because throughout the semester, I'm going to be using these words. So if you are clear about what they mean, then it will be easier for you to understand what we are discussing. So the first one is called an entity. And the entity is basically the object of interest for our simulation. Most of the time, that's what's being moving from station to station, or the object that is being transported from one point of the, let's say, the warehouse to another area. So anything that is moving through your model most likely is our object of interest, and that's called the entity. So for example, in a manufacturing process, if you are looking at producing certain items, those items are going to be the objects of interest. We want to know how many you're producing, how long does it take for you to complete them, and so on. If you're looking at the service environment like a hospital, then most likely you're looking at patients. Patients are going to be the object of interest. Same thing if you're looking at the airport, passengers are going to be the object of interest, and so on. Okay, so that's what we're going to be calling an entity. And then we have an attribute, which is going to be a property of those entities. And these are very important attributes. They don't change. So once you assign them to a entity, most likely they're going to stay with that entity for the rest of the simulation. Like, for example, if you're looking at a manufacturing process and you want to know when the part arrived to a specific station, you can assign an attribute that will state arrival time to station 1, and then you're going to record that time and you're going to assign it to the entity. And that attribute arrival time to station 1 will be with the entity through the simulation model, through the running process of the simulation model. And if at any time you need to know what was the value of that attribute, you can call that attribute and get the value. Okay, so things like colors could be an attribute, arrival times could be an attribute, size. Let's say you're looking at different sizes of boxes. You can define an attribute saying box size, and then you can assign a value of 1. If it is small, value of 2. If it's medium, value of 3. If it's large, that attribute will stay with the box. Most of the time we're gonna have, like if you're looking at service environment, let's say you have different type of passengers in an airport, like business class or general class. You can differentiate the passengers using an attribute, passenger type, and then you assign a value to the different types, and then you can classify them and use that information. Let's say if you are looking at a line that is specifically for business class, you can differentiate those passengers and then assign them to different queues in your model. Okay, so those are some of the important things related to an attribute. A model, this is something that we briefly discussed yesterday, is an abstract representation of a system. So what we're going to be building in a computer is what we're going to be calling a model. A system state is a collection of variables that contain information necessary to describe the system at any time. So for example, if you're looking at a specific machine, you know, there's going to be different states in which that machine can be, like busy, idle, under maintenance, and so on. So we can specify the different states in our models. And then based on the state in which that resource is, we can make decisions. Like if it is idle, I know I can send a part to that machine to be processed. But if it's busy, I know I have to wait, right? So that's the important thing about those states. Yes, sir.
Would the system state be an attribute of a particular machine, or is this a different?
That's a good question. So we have to make a differentiation between attributes and variables, and I think I have the definition for the variable at the bottom. Variables are, in a sense, an attribute that can change values, right? So that's the main difference between an attribute and a variable. An attribute, that information is not changing. A variable, it will be changing value according to the processes that you are observing. So the system state will be a collection of variables that will be changing according to the time and the actions that are happening through the system. Good question. An event is an instantaneous occurrence that changes the state of the system. So for example, if you're idle, you get a part. At that point, you're going to be changing your status from idle to busy. If you're running a process and then suddenly something outside what is normal happens, maybe the machine will go into failure mode. That's a different state, different process in which, you know, there's certain things that needs to happen for you to continue your production. All those things are coded within the software package, right? We just need to know how to interact with them according to the logic that we want to execute. We have an event list or future event list. These are the sequence of events that we are going to be using for experimentation. Like, for example, if we want to run a process for 8 hours and we want to understand the performance of the system for 8 hours, the software package, as obviously is going to require some input from the user, but it's going to generate a set of events for those 8 hours in which you're going to be testing the performance of your system And then at the end of those 8 hours, we're going to observe, okay, based on this event list, this is the performance of our system. And then we have a clock, which is basically a simulation time that we are keeping track of. It's representing actual time, but in a computer, right? So it's an artificial clock. Obviously, it's moving faster than our clock or our typical clock. And the idea is to build the sequence of events that are based on time within the computer model. This clock we can also call at any point during the simulation model. So during the execution of the simulation, like for example, if I want to know the arrival time of an entity to a particular station, I can call the clock, see, okay, tell me the time right now because I know the part just arrived and I'm going to record that time. We use a variable that is called tnow, and this is a software name, right? It's a variable that is coded within the system. It's called tnow, and that's the variable that we call if we want to know the time at any point during the simulation. And then finally, we have a variable which is information representing some system characteristic, and that can change throughout the simulation run. Any questions? Okay, so this is not something that you need to memorize. This is just mostly for you to get familiar with the concepts. Yes, sir.
So whenever you're looking at how entities can interact with each other within the system, what holds the rules of interaction? Does the system hold the rules of interaction for the entities within it, or do each entity hold the rules for its interaction with its surrounding?
Okay, so entities basically are going to be following the logic that you implement for them in the code. So most of the time they're going to be following a sequence, right? That you are determining based on the logic. And this type of sequences will have several things that are going to be based on whether or not you need them for the problem that you're studying, like things like a queue, for example. So, you know, if the system is busy, most likely you're going to need some type of queue to hold these entities. There are other logic components such as signals and release in terms like, for example, if you're representing a traffic light, I would say that you need to wait for a signal for you to move. There's some other logic blocks that you can use to guide the entities to what they need to go and move within the system. There are other type of simulation environments, for example, agent-based simulation. So I guess that's where you're getting to, in which you can program some of these behavior inside the entities. That is outside of what we are trying to do here, okay? So agent-based simulation is outside what we are focusing on discrete event simulation models, which are typically more connected to what you observe in a manufacturing environment. But I think I know what you're referring to. Any other question? Good. Okay. So that being said, I have a slide here. This is, again, just a suggestion. The idea is for you to make sure that you save your model as you are constructing your simulation model, because Arena doesn't have a autosave environment. So this is something that I have observed a lot of times, students being almost done with the simulation model that they're building. They forgot to save, system crashes, they need to start again. So make sure that at some point from the beginning, you create an environment, a location for you to save your model, and then you are aware that you need to save your progress as you move forward. because things like that will happen. At some point, the software might just freeze and you need to restart it. You will lose your progress, maybe need to start again. So in order to avoid that, make sure that you save. So you'll be submitting your labs online. I'm gonna be grading them. So I'm also suggesting here a saving naming convention. For example, lab number, your last name, .doe. The DOE environment or the file type is for the simulation. That's the Arena extension. So in my case, I'll be lab1 Paris.doe. This is very helpful. I have only 6 students, so I think in this case might not be a big issue, but if I have the last name, it's easier for me to connect your work with the grading table that I need to give for you to see your grades online. Okay, so that being said, now I'm going to talk a little bit more about the setting up within the model. There are certain things that you need to set up in order to get to work with the modeling and building your model. And I don't know if you guys are already were able to access Arena in the computers. You were able to get it?
Yeah,
Arena?
I'm opening.
Okay, good. So there are, and I know they might be different versions of the Arena. I'm not sure. I asked for the latest one on these computers, but I don't know which one they end up installing. So I have Arena 2022 in this computer. At the end, it's very, I mean, all of them are very similar, so it's not going to be an issue.
Do we need to manually add the DOE?
It should be by default when you're saving your model. Okay. Okay, so one thing I think from your seat, you can look at the main environment. Maybe this is what you're seeing in your computer as well. So what we have here is an area towards the left in which you are gonna have your modules to build the models, right? So that's what we call the project bar. So the way Arena works is you have a group of blocks that you drag into the main area, which is this empty area here, white empty area. If you see the tab in green, it says model 1. That's by default, but once you change the name of your file, it will change to the name of the file. So what we do is we drag some of these blocks to this side, and we start inputting information into those blocks and connecting those blocks in a sequence that will represent the problem that you are trying to represent. So this is going to be changing through the semester. I'm going to be starting with the basics blocks, and then as we move forward through the semester, we're going to be using some of this different set of templates. The other thing that you have here are different tabs like home. You'll get familiar with this. For the home portion of the environment, the most important ones are this group right here, which says connect. This option will allow you to connect the blocks into a sequence. So you'll be using this a lot. And then this group right here is to check the model for errors, to review the errors, and then this little buttons here, play button and so on, is for you to run the simulation. So when you're ready to run the simulation, you will click the play button and it's gonna run the model. If it is with no problems, no errors, it should show you some results. If you have errors, then it will display a list of errors that you need to change or revise before moving forward. Then we have a tab that is for animation purposes. So I'm going to show you how to use this, maybe half through the semester. I'm going to start incorporating some of the animation in Arena. But it allows you to do things, simple things like creating a clock, a calendar, charts, representing queues, representing storage, resources. Like for example, if you have a machine, you can create a image of the machine that you're using and represent the different states of the machine. And then as you run the model, it's going to be changing according to the status of the machine, routes, and so on. So we'll be looking at some of them in class. This we don't use as much unless we want to type something for the user to see in the model. Like for example, if you want to state, okay, this is the model area, this is the experimental frame area, we can use that option to type. The run environment, here's where we're gonna set up our experiments. So we will use that today. And then the rest of them are very straightforward. The view, just zoom in, zoom out, and some of the tools that are there in terms of macros and so on. So we're probably not gonna get to that level in this class, but we'll see. That's the main environment that you are gonna be using to build your models in Arena. Now, let's look at some of the modules. Let me start introducing some of them. Okay, so first, the way that building any discrete event simulation model, it doesn't matter which software package you're going to be using. You have two main components. One of them are the resources that are going to be available in your system. And then the second thing is the entities that are going to be using those resources, right? So first thing I'm going to show you is how to build a list of resources that are going to be used in your simulation. So as I mentioned, if you're familiar with Arena, maybe you're not familiar with these specific blocks that I'm going to be showing today. If you are, great. If not, don't worry. We'll get to the new ones as we move forward through the semester. But the reason I show you this first is because these are the first set of blocks that were developed within Arena. And these, if you look at and I'm going to show you that there's a big list of models, of blocks and elements that are, as you move forward with the development of the software, some of them were discarded or deleted. And that kind of put a limit in terms of the type of logic that you can build right now in Arena. So the purpose of showing you these blocks is to give you more flexibility when you're building your models, because these all templates provide you with a lot more flexibility than when building models than the current ones. Current ones are more designed towards making the software user-friendly, right? But it loses a lot of flexibility in terms of the things that you can do in Arena. So we'll start with this group. And then if you at some point are working with the newest templates and you see, oh, I know I can do this, but there's no blocks in this environment, you can always combine the old ones with the new ones, which is nice. It's a nice thing that you can do in Arena. You can use the old blocks with the new blocks and it will work. Which is typically what I do. I use the new ones. If I need some extra logic, I go back to the old ones and I add them and I combine them. So we'll start with the resources, and the way this group of templates, the original ones, work is you have two groups. You have a set of elements in which you define your experimental frame. The experimental frame is where you are basically setting up your experiment. So here's where you define these are the resources, these are the statistics that I'm going to be using, this is for how long I'm going to be running my model, and so on. These are the queues, these are the statistics that I want to collect, and so on. So we'll start with the elements. For resources, these elements define the characteristics of the resources, including the resource names and the initial capacities. A capacity represents the number of identical units of a resource that are available. Okay, so something that I want to highlight here is that word identical. So if you have identical resources, let's say machines that are the same and they're in the same station, and you can use either one when you're producing an item, the first one that is available, but you're sure that they're identical, you can easily represent those here by just changing from 1 to 2. Say instead of one machine, I'm going to have 2 because they are identical and they're going to behave the same way. Only if they are identical, right? If you're looking at a cashier, right, you know that 2 people would not behave the same way. So if you want to represent 2 cashiers instead of 1, you cannot use this, right? You're going to have to represent them separately as independent resources, right? So that's the main thing. If you have identical resources and you want to build a logic with those identical resources, you only represent one of them in terms of building the resource. But if you have more than one, you can just adapt the capacity here. If you have resources that are different, then they need to be modeled differently. Processing times are going to be different. Maybe the number of people they can handle or the number of entities they can handle at the same time is going to be different. So they need to be built separately, which means that you're going to provide different names for them, right? So in this element, what we're going to be doing is just naming and identifying and listing how many of them we have. So we have 2 machines that are identical. I'll call this machine, and I have 2. You have 2 machines that are different. I want to have machine 1 with capacity 1, and I have machine 2 with capacity 1 as well. Okay, so that will make more sense once we get into the model. And then we have a resources element, right? So I'm going to start writing here, experimental frame. So first thing I'm going to have is resource. So this is going to look like a block. And then I'm going to have my model here at the top. So once I define a resource, let's say I call this resource machine or machine 1. And I only have one of them. I want to build a logic now that will represent this machine. Okay, so I define the name and the capacity. Now I want to build the logic. So to build a logic for a resource like a machine, we're going to need 3 blocks. The first block is called the C's. So this uses a resource and remove it from the list of available resources. So what this does is, let's say an entity gets to this block and is trying to use a machine. What this C's block is going to do is to check if a machine is available. If the machine is available, it's going to assign it to the part, or the part is going to be assigned to that machine. If the machine is not available, it's going to be return it to the queue, or make it wait into queue. Right, so that's all this does. So for example, carpenter uses a hammer. The hammer is no longer available until the carpenter is finished with it. Right, so you cannot assign the hammer until it is returned again. So that will be the C's. So in this case, I'll have, and I only have there's a blue other works. So there's gonna be a C's, and I'm gonna be trying to seize this machine work. When the part arrives here, I'm gonna try to seize. And then if I'm successful seizing that machine, the next thing is gonna happen is we are gonna use a delay block to represent the processing time for the machine. So the machine is gonna process this part, or the cashier is gonna check out this customer, right? That's gonna be a time associated with it. That's gonna be represented by a delay. Another thing, you may see worker goes on a break for 30 minutes. There's a delay of 30 minutes into the process. So what's next here, once you see is that machine is a delay. And most of the time, this is represented by a probability distribution, like a normal distribution, triangular distribution. Okay, so because there's some variability in how long it will take. So let's say this is normal. It's making up some numbers, right? So it's gonna be 2 minutes with a standard deviation of 1. And then after that processing time is completed, we release. So there's another block here. And then release machine 1. So at this point, this machine becomes available. Once you release the machine, it becomes available for the next part that is in the queue. Okay, so if we are representing a machine or any resource in our model, we have to use these 3 blocks. Seize, delay, release, and most likely there's gonna be a queue associated with it, which is another block that we are gonna define separately, which is gonna be holding those parts in front of the resource. So I'm gonna talk about the queue in a minute, but I just wanted to connect how this would look like for a machine. All right, so we define the experimental frame, the resource in the experimental frame, and then we use that name to define the seize and the release, but in between we need a delay for representing this resource. Okay. Another group of elements and blocks are for statistics. So one of the statistics that most of them we collect is called the number of parts completed, right? So typically we use a counter or counters element experimental frame here. We're gonna define counters. And this is a list of counters for our model. So if you want to count different things, you're gonna need the different things that you're gonna be counting here in this element. Like for example, parts completed. That could be a counter. And then the way you implement the counter into the model, you have a block that is called count. and it's gonna be using this name box completed. So at the end, once in this case, once they have gone through the processing, you count them as parts that has been completed, part that's been completed. So the count block increments the counter specified by a counting ID by the value of the operand counter increment. So the default value for the increment is 1. So every time something crosses that block, you increment the counting by 1. But if you want to increment that counter by 2, you can also do that. Or by 3 or by 4, we can change that in the logic. Okay. There are 2 other things that we are gonna need. I'm sorry, I don't know why it's not here. So we are gonna need the experimental frame. We also need to define our cues. Right, so in this case, it's the same thing. We can say Q1. And then when we call the Q block, we are going to be using that same name to define the Q. And this is how a machine model will look like. There are 2 additional blocks that will be needed to complete a model. Those 2 blocks, they don't need to define anything in the experimental frame. Those are blocks that are default for all the models. The first one is called dispose. So the dispose block is gonna be used to delete those entities that are not longer needed, just to save memory space in your computer. So if you no longer want to save the information that is inside each one of those entities, let's say you have 1,000 entities, you don't want to hold onto them if you don't need them, because those are going to be occupying a lot of space in your computer, and this is going to be running for long times, right? So we don't want to occupy space that is not needed. So we use the dispose to discard the entities that are no longer needed, so we can have space. And the other one is called the create block. And this is basically the block that is going to be generating the entities that are going to be arriving to your system. Typically follows a probability distribution, like exponential 4 minutes. And that distribution is representing the inter-arrival times, the time in between arrivals, right? So if I say 4 minutes, what that means is entity arrives now, the next one is going to arrive in 4 minutes, the next one is going to arrive in 4 minutes, and so on. Obviously, there's going to be variability associated with those inter-arrival times, so that's why we model them using a probability distribution. Okay, so this is a model. This is basically what we're gonna be building now in Arena. Any questions? Oh, that's yes.
So far we're passing containers, but we're doing nothing to what the containers are holding inside, right?
What do you mean?
It's like the create is creating an entity.
Yes.
And it's just like a box, but we don't really care what's in the box right now.
No.
We're just passing.
Right now, we're just saying all the parts are gonna be the same. And they're gonna wait here until these machines are available, the machine is available. And they're gonna be processed in this machine. And then after that, they're counted and eliminated. Right, so what we wanna know is if we have these arrival process. And we have a machine that has this processing time for a period of time of let's say 8 hours, how many parts we can produce under those circumstances. Yes.
So, thank you.
Any other question? Good. So this is the example that I want to build with you today. What we have again is a very simple process in which we have parts arriving into this drill, which has this processing time, follows a triangular distribution. The triangular distribution has three parameters. The one in the middle is the most likely, the minimum, and the maximum, right? So these are processing times. So most likely it's gonna be processed in 4.2 minutes, but could be 3.2 or 5.2 based on the uncertainty. And then the arrival times, each arrival times are going to be represented by an exponential distribution. And the idea is to count how many parts are completed in 8 hours, which is basically the model that is presented on the board. So now we're going to build that in Arena. So let's see how that goes. Okay, so first thing, we need to get access to those templates. So what I want you to do is to take your arrow, place it on top of this area, the project bar, and do a right click. You will have 4 options. I want you to go to the last one, template panel, and then click attach. And you should have this window or this folder open, right? Yeah, so as you can see here, these are different templates for Arena. The ones that we're going to be using today are the blocks.tpo and the elements.tpo. So you can click blocks, open, and then template panel, one more time, attach, and then go to elements. So in addition to those templates, we now have the blocks and the elements. So if you need to use the blocks, you can just click on top of that word and it will open the blocks. And if you need to go back to the elements, you click on top of the word elements and it will go back to the elements menu. But it was able to get to that point. Great. Yeah. Okay, so I did there. I want to make sure that you understand that there's a difference between these two sets, right? So that will be represented also in the model. So I'm gonna go here to the draw tab, and I'm gonna use the text type model. And I'm gonna increase the size of that font. So if you want to increase the size of the font, you can just click here. I know by experience that the default is very small. So I switch to 12 just to make sure that I can read the word model. And then I'm gonna do the same thing. I'm gonna write now experimental frame. And that is 12, so we are okay here. So I'm going to start with my experimental frame. And I'm going to be using the elements. So in this case, we're going to need queues, resources, and counters. Right, so that will be the case for most resources. You're gonna need the queues and I mean, for all resources, you need queues and resources element. Counters will be depending on the statistics that you need to collect. For today, we are gonna be collecting only the number of units. Next time, I'm gonna show you how to collect some additional statistics. So I'm gonna go here and I'm gonna find the queues. So these are listed in alphabetical order. Right, so I'm gonna pull queues here. I'm also looking at the resources and also looking at counters. Queues, resources, and counters. If you don't find them, most likely you're in the blocks. So you have to look into the elements. Can I move forward or you okay? Okay, so let's start with the queues. When you double click here, you double click that block, this is the menu, right? Very simple. I want to add a name, right? So I'm gonna click add. And these are default values. The only input that is required, every time you see a menu like this, inputs that are required are the ones shaded with the dark gray color. Those are required, right? So here, the only thing that is required is for us to define a name. The default name is Q1. I don't like to leave space in between the words that are used to for naming purposes. Arena is case sensitive. Like if you use capital letter, then capital letter. You lower letters, lower letters. You use space, you need to represent the space. So for me to avoid any typos when I'm writing, I like to write, if I have two words for the name, I'd like to write them together and I differentiate the words with using a capital letter. So for example, a machine Q. So that's my strategy. If you have a strategy that works for you, you can use your own strategy. You don't have to use mine. But again, a lot of problems will result if you don't have a individual strategy because of the case sensitivity of the software. So machine queue, first in, first out is the ranking criteria. So it's not changing in this case, but you have options. Last in, first out, low value first, high value first, in case in a case in which you have an attribute, let's say 3 different parts, and you want to make sure that part type 1 is always first, you can do that. For now, we're just going to use the default, but later in the semester, I'm going to show you how to use these different rules. First in, first out is FIFO. Last in, first out is LIFO. Which is the same thing as these first two. I don't know why they have them separate. Yes, but they do the same thing. Yeah. So in case you're familiar with the letters, you can find them. Anyway, first in, first out, default, and then click OK. What you're gonna see now is that name for the queue is gonna show up here at the bottom. Right, so machine queue is now here. So that means that you have one queue with name machine queue. Next, we move to resource element. And again, same environment. I want to add a resource. The only thing that is required is the name again. But there's a couple of things here that are important, specifically when we are looking at the capacity. Right, so there's two options. For now, we're going to be using the default capacity, but there's an option in which you can use a schedule, meaning that the capacity of that resource will change throughout the day. Like if you have an employee that is taking a break for lunch, you can change that. And then halfway through the day, the capacity will go to 0 and then we'll go up to 1. For now, we're going to use the default capacity. And then that one right there is very important for you to understand what that means, because you're going to be using that for the assignment. Remember when I mentioned that identical machines, if you have identical machines and you have more than one, you can just come here and say, I have 2 of those machines. I have 3 of those machines. So in this case, if we have two machines that are the same, we can just change that capacity to 2, and the model will know that you have 2 machines that are identical. Okay, so here's where you go to change the capacity inside the elements, resources, right? I'm mentioning this because you'll see when you get to the model, there's one item there that could be confusing, and I've seen that errors many times, so that's why specifying identical machines, changing capacity, you go here. Change that capacity to 2 or to 3, depending on the number of machines that you have that are identical. And I'm gonna change the name to drill, right? Because I have only one drill here. Drill capacity 1, okay. And then I have the counters. So I'm gonna be counting parts completed. So I'm going to add here, same thing. Only thing that is needed is the name. So I'm gonna change this name to parts completed. Yeah, for now that's enough. Parts completed. So this is how your experimental frame will look like. You have 3 blocks here, PQ, drill, parts completed. Any questions? Good. So now let's move into, okay, I don't want to be the one getting the model deleted, right? So I'm going to be saving this. So I encourage you to do the same thing. So model. And I'm going to save it. Do you see the tab just changed names right there? Okay, so let's go to the blocks and let's build our model using this information. So what I'm going to do is I'm going to find these blocks that are right here, and then we're going to edit the logic for them. So I'm going to start with the create. Here's where we are going to create our entities. Then we go to queue. And sometimes when you add the blocks, the model will connect them automatically. If it doesn't happen, don't get scared. It doesn't do it every time, right? So it will do it for certain combinations. If I go to C's, like for example, it didn't do it there. Delay. release. And then I have the count. And finally, the dispose. Okay, so create queue, cease delay release, count, dispose. So let's start with the create. Double click. This one, it doesn't show you what's needed. I think this is the only block that is not forcing you to write something. So for this one, you will need to remember that probability distribution has to be written here in the interval. You can also specify when the first creation is going to happen. Like if you want the first creation to happen at time 0, you can tell them time 0 or time 10. Right. So for now, we're going to use the default. And then you can specify the batch size, how many parts are going to be created at the same time, and the maximum number of entities that you want to create. So for the interval, as you get familiar with Arena, you will notice that when you are defining a probability distribution, you will use the first 4 letters of the name of the distribution to assign the distribution to the logic. And then you have some parentheses. Inside the parentheses, you put the parameters of the distribution. But as you get familiar, you will do that automatically. For now, I encourage you to use the build expression. Like if you go here to interval and you select build expression, you can go to the option for random distributions, and you will have the list of probability distributions that are available in Arena. In our case, we're going to be using the exponential. So if I click on the exponential, you will see that the expression is going to be built for you. The only thing you have to do is to specify the parameter, and it's telling you which parameter you need, right? So here we go here and tell, well, is 4.4 for this model. So go to random distributions, click on the distribution that you're going to be using. You input the parameter and the expression is going to be built for you. Then you click OK, and you see that expression is right there. Then you click again, and it will show you the Expo 4.4. Questions? We're good? And we are using an Expo 4.4 because that's what we stated here, right? So that's why we are using 4.4. Next, we have the queue. QID is the only thing that is needed, right? So in here, once you define the names in the elements, if you come here to this drop down menu, the name that you define is already there. So the only thing you have to do is to choose the right queue. In our case, it's machine queue. The other thing that is important here, which is also important for your assignment, is the capacity. You can put some capacity limits into your queue. Like for example, let's say you have a conveyor that can only hold 10 parts. You can say you can only hold 10. You put a capacity of 10. What's going to happen with the entities that come in and they don't find capacity? They're going to be sent through another output. So let me show you. So if I put a capacity here, the entities that come after the capacity is full will go through. This is the only block in Arena that has 2 outputs. It has the output that connects to the next process, and it has this output for discarding entities. right? So if you have a capacity of 5, entity number 6 come in, and you have 5 entities already, number 6 is gonna go through this block, this portion, or this output. Yes.
Connected to other blocks?
Yes,
Okay.
exactly. So that's what you will need to do for the assignment. I want you to count how many parts are going to be discarded from each process. So in that case, you're probably gonna need to define another counter. You're gonna put that counter here. And then you are going to connect this to here. And then this to here. So the parts that are finding space are going to be moving forward. The parts that are not finding space, they're going to be counted as discarded by the process. Good questions. But we don't need it for the example. And again, we're going to have time. Oh, well, not necessarily. Okay, so typically I will have a lecture in between the day of submission. Like in this case will be Monday, but Monday is a holiday. So I will answer questions on Monday so you are ready to submit on Wednesday. So if you find yourself with questions, send me an email. We'll have office hours tomorrow if you have the time to look at it today, the assignment today. Maybe you want to stop by the office tomorrow. But if not, we can meet on a separate time on Tuesday before the submission. Okay, so going back here, we have Shinkyu, and then we're gonna deal with the resource, right? So first we need to see when you double click, this is the menu. Again, typically what we're gonna do is to add, right? So we're gonna click here to add the resource associated with this process. You go to drop down menu, you select your resource. And this is what I was referring to. Most of the time, well, not most of the time, but I'll see some students, if I ask them to, if they have 2 identical machines, instead of going to the elements and change that capacity to 2, they'll come here and put 2 in the number of units. This number of units, what it means is how many units you need to start the process. Like if you put 2, that means that you need 2 entities to start processing them. If you put 3, then I need 3 to process, right? So changing that from 1 to 2 is basically telling the system you're going to be processing more parts together or at the same time. This is not changing the number of machines that you have available. Okay, so we're going to keep it in 1. We're going to just assign the name of the resource. And then click OK. And everything is getting recorded. Okay, so you can watch the video also if you have questions. For the delay, we need to update the duration. So I'm gonna go here to build the expression, go to random distributions. And as I said, we're gonna be using a triangular. So we have the minimum value, the most likely value, and the maximum value. So if I remember correctly, the minimum was 3.2, most likely was 4.2, and maximum was 5.2. Let me just double check. 3.2, 4.2, 5.2. Yes. So we input the parameters, we have the expression. And then click OK. And then for the release, we do the same thing that we did for the C's. We're going to add, we're going to find the resource. And the quantity to release is 1. So how many units do you need to release this part? How many parts needs to be completed for you to release this machine? 1. Then click OK. almost there. Let me save, make sure that everything is getting saved. Then the counter, we already defined the counter name. So we are gonna find the name for that counter. And here's where we have the counter increment. So if you want to increment by 1 every time a part crosses this block, you keep it with the default. If you want to increase by 2, by 3, depending on your experiments, you can change that here. Okay, so save. So once you are done with the logic, there are 2 more things that we need to do. First, we need to check if we have any errors, right? So if you go here to the Home tab, there's an option, or you can just hit F4, press F4. It should run the check model for you. So if everything goes well, you should get something like this.
No, we didn't define the simulation, if we're running without definition, I'll just keep running.
Well, yes, exactly. So we need to set up the parameters because if not, it's gonna run forever, right? So first thing, you check the model, it's good. Any errors? No, good. Now we need to set up the experiments, right? So for that, we're gonna go here to run, the tab named run. And there's an option here called setup. There are multiple things here that we need to take care of. Like, let me start with reports. The report that I want you to generate in this class is the Siman summary report. The reason for that, if you don't select that report, you're gonna get a report like with 20 pages, and then you're gonna have to fish the information that you need. So I prefer to generate the report with the statistics that I need, right? So for that, I need to use the Siman summary report. So I click apply. I select Siman, I click apply. Then I move to the parameters. Here you can change the name. Let's say example 1. You can put your name. And then for now, I want you to uncheck all this. And then click apply. And then the last one will be the replication parameters. Here's where you define for how long you want to run this. So you go here to replication length. We can put 8 hours. Something that is very important is for you to select the base time minutes, because everything that we input into the model right now is based in minutes, right? So you need to make sure that you tell the model the units inside the system are in minutes. The replication length, it can be in any time units, but the base time units should be minutes. And we're going to talk about the warm-up period later this semester. For now, let's just click and let's try to run this. You can hit the play button here on the run. It will ask you, would you like to see the results? And this is what you're going to see, hopefully. So in 8 hours, we are able to complete 105 parts. Okay, so I want to do something with you now. Everybody got this number?
Yes.
Good.
I did not click on the bottom, but they set up the capacity on the queue. Did we do that?
No, no capacity. Yes. So if let's say instead of 1 drill, I have 2 drills. So I'll go here to resources. I'm going to edit this capacity to 2. What do you think is going to happen? Well, Not necessarily because you have an interarrival time, right? So there's some situation right there, like it's time dependent, right? So we'll see. So if you have double the capacity, see.
Yes.
It's less. Huh. Why is that?
You're giving it to.
The only thing I did was to increase the capacity to 2. And it went down. That's interesting. Let me change the number of each replications and see what happens.
It would be just like noise.
So now it would make more sense, right? So again, as I said, there's uncertainty in the system, right? Every time we run, we change the parameter in the system. And this is more connected to the statistics side inside the model. So now I ran 2 experiments. They're using different seeds for the random number generators, right? So one is 116, the other one is 96. It is because of the uncertainty that is caused by the interarrival times and the processing times. So that difference in the numbers, what I want you to see is like sometimes we try to use some intuition to make sense of the numbers. When you see that something is not following your intuition, try to think a little deeper on what can happen with the information that you're providing to the model. Yes, sir.
Is the seed gonna be randomized the same way each time?
So every time you change, like for example, if we all have the same model, we should get the same result,
Okay.
right? But if you change the parameter like we just did, we just switch from 1 to 2, that random number generator is now doing other things.
So is the seed dependent on all of the parameters in your system?
It will be, the same seed will be used for all the input parameters of the system. Yes. Yes. Good. So that's all I have for today. I'm gonna stop this now. I'm going to save the video.
The function of that button you just hit right now.
Say that again.
What is the function of that button? You just hit. Yes.
This one?
No, right. Again button. That's the end button. So.
Oh, this one? Yes, to stop.
So every time you need to stop that.
Once you're done, yeah, if you want to run it again, you have to stop it. Yes.
Stop and you can change the parameter.
Yes, exactly. Yes. Any other question?
Whenever I'm checking the files that were created from the